Good morning, everyone. My name is Yuping Wang, and today I'm excited to present UniOcc, a unified benchmark for occupancy forecasting and prediction in autonomous driving. This is a collaborative effort from the University of California, Riverside, University of Michigan, University of Wisconsin-Madison, and the Texas A&M University. Our goal is to provide a comprehensive, all-in-one solution to accelerate research in 3D occupancy for autonomous systems. Current research in 3D occupancy faces three major roadblocks that are holding back progress. First, we have a problem with suboptimal labels. Datasets like nuisance and Waymo do not have official occupancy annotations, so we have to rely on pseudo labels generated from sensor data. As you can see here, these labels are often incomplete, capturing only the surfaces hit by the lidar. This means we are training on flawed data, and standard metrics can even penalize a good model for predicting a more complete, realistic shape. Second, our models are trapped in data silos. A model trained on nuisance won't perform well on Waymo because of differences in sensors, data formats, and environments. This lack of generalization is a critical safety issue for autonomous vehicles that need to operate reliably in new situations. Finally, we have a lack of paradoxical flow. To predict the future, we must understand the motion. Current methods oversimplify this by assigning a single velocity vector to an entire object. This approach completely misses complex dynamics like rotation, which fundamentally limits the accuracy of our forecasts. To solve the problem of suboptimal labels, we take a two-pronged approach. First, we augment our real-world data with perfect geometric labels extracted from Carla simulator. This teaches the model what complete, realistic objects look like, overcoming the limitation of sparse lidar data. As you can see in the comparison, the model trained with Carla data produces a much fuller, more accurate car shape. Second, we introduce novel ground truth-free metrics. This assesses the quality of a prediction by measuring its shape realism and temporal consistency, giving us a more reliable way to evaluate performance without relying on the flawed labels. The second part of our solution tackles the problem of fragmented data. As the diagram shows, a model trained only on nuisance fails when deployed to a new domain like Waymo. To fix this, we develop a unified pipeline that standardizes and merges major datasets. This allows us to train our model on all available data at once. The results are clear. As shown in the table, training on the combined nuisance plus Waymo dataset consistently improves performance. This proves that diverse, unified training is key to building robust models that can generalize to new unseen environments. Finally, to address the lack of true motion dynamics, we introduce paradoxical flow annotation. We are the first benchmark to provide these granular motion vectors for every single voxel, capturing both the movement of dynamic objects and the apparent motion of the static environment caused by the vehicle. The benefit is significant. As the table shows, training with our voxel level flow leads to state-of-the-art performance, boosting all key metrics, including an over 10% improvement in background consistency and an 8% increase in car shape realism. So to put it all together, this is the UniOcc framework. We take data from multiple sources like nuisance and Carla, process it through our unified data pipeline, and use it to support both occupancy prediction and forecasting tasks. Our framework also includes a comprehensive toolkit and our novel evaluation metrics to create a complete end-to-end solution for occupancy research. In conclusion, our experiments show that UniOcc successfully addresses the key barriers in occupancy research. Our unified dataset, ground truth-free metrics, and paradoxical flow accelerate the development of more robust and generalizable models. Whether you are a veteran in the field or a newcomer, UniOcc provides the tools and data to push your research forward. Our future work will focus on bridging the sim-to-real gap through principled domain adaptation and targeted scenario generation. We invite you to check out our project website to access the data and the code. Thank you.